Okay, good morning everybody. You're almost done. Why do they always leave the hardware guy until last? I don't really understand that. So Victor introduced himself with a story about running, and I have my own story about that. At one point, Victor suggested that I might want to run a marathon with him, and look at me. Is this a likely scenario? So he said, I'll give you an option though. You can decide where we run. And I said, okay, I'm Irish. Why don't we do it in Dublin? And my thesis was simple. If I took him to pubs for the 2 nights before we went on the marathon, I might have a chance. Suffice it to say, he got home, I would say, in enough time to shower, have a nap. I eventually turned up. So that's my only story about marathon running with Victor. I'm delighted to be here today. I've been looking forward to this for 4 years or so. Because basically 4 years ago, we decided that we needed a new architecture. So I took some of our key engineers, some of our key architects, and we actually moved them out of our core engineering building into a remote site. And the idea was we wanted them to really rethink how we build chips and also how we think about FPGAs. And in doing that, I think we really rethought the whole underlying architecture. And today I'd like to present what came out of that. So, in thinking about the new architecture, we realized we were in a different world than we'd been in before. Essentially, it was the world of big data. And, when I think about big data, I think about the 3 V's. That's the way I remember it. So the easy one is volume, right? There's a lot of it. The second one is variety. It comes in many, many different forms and shapes. We know that we, for example, have audio data, video data, and the like. And last but by no means least, velocity. We're creating data at an incredibly fast rate. And because of that, we have to be able to process it very quickly as well. And I think Salil gave you some great examples of how you want to chew on the data in a reasonable period of time because of the rate that it's being generated. So, when I think about how much data there might be, I looked it up on the web, as we do. And I think by 2025, they're estimating there's going to be about 160 zettabytes of data. Or to put it in perspective, 1/6 of a yottabyte. Probably doesn't help, does it? So, I was thinking about this a couple of years ago. I was preparing a talk I was giving at IEDM, and I said, I have no idea what a yottabyte is. Happened to be watching the Summer Olympics. They were playing beach volleyball, as it was. And I thought, well, if 1 grain of sand was a byte, how many grains of sand would it take to have a yottabyte of sand? Got out my calculator, did a few calculations, and the answer I got was that if you had a beach the size of California that was 50 feet deep, that would be the equivalent of a yottabyte of data. So, obviously quite a lot. The other thing we looked at was, what sort of architecture should we implement? And in doing this, one of the first things I asked the team to do was say, what if we took our 16 nanometer architecture and simply took it to 7 nanometer? Somewhere in the world, people have this idea of tick and tock, so let's give that a try. How hard could it possibly be? Fairly difficult these days, by the way, just in case you didn't know. But anyway, the bottom line was that what we did was we took the 16 nanometer architecture and we shrunk it, and we found we got improved power. But when it came to performance and cost, as Mark Papermaster pointed out, wasn't looking too good. So we used that sort of as our benchmark for what we would do in our new ACAP. And in seeing that, what we realized was that the work we'd done over the last number of years in heterogeneous architectures was the way to go, but we needed to take it to the next level. So, we obviously wanted to understand what you, the developer, needed. I think Salil did an amazing job of talking about how we've become software-centric. Now, many of you out there may still be RTL designers, but believe me, there's just huge opportunity in going to the next level of abstraction, in getting a lot of improvement in productivity. We also realize we have a diverse range of applications. We go all the way from the cloud, through wired, through wireless, to auto. So we had to have an architecture that was going to be able to support that. Last but by no means least, we know adaptability matters. And that's the only way that you're going to keep up. I think the last two speakers, both Victor and Salil, have driven that point home. Who wants to be locked in to something that is 2 years old? It just doesn't make sense. So in looking at that, we looked across the landscape of available heterogeneous solutions. CPUs, as Mark pointed out, are really plateauing in terms of performance. And we all understand why that is. Moore's law has pretty much run out. On top of that, if you look at what happened in the early 2000s, people decided that, hey, what we'll do is do multi-core. How hard could it possibly be? What you probably noticed is that people haven't really implemented anything more than, say, 20, 30 cores. And the reason for that is a guy called Gene Amdahl, who in 1967 noted that if you had a very small amount of serialization in your program, it completely messed up any parallelism that you had. As an example, if you had 32 cores and you had about 10% serialization, it's a relatively small amount, you would end up getting about 25% of the peak performance. That's a pretty sobering story, particularly if you build CPUs for a living. Obviously, you have to do something very innovative, which I think is what AMD did in your approach to building them. The other thing we should talk about is fixed function. I think we've already talked quite a bit about GPUs. Again, we've seen that with ASICs and ASSPs, you can optimize a specific application. But when it comes to broad ranges of applications, or ones that are changing, clearly you're in trouble. And then our own FPGA, right? Very adaptable, clearly has a lot of advantages, but as we said, there were some issues in terms of high-level programming and making it friendly to the software community. So I'm just repeating a slide that Victor had, but just to dive down a little deeper to what we have done in about the last 6 years or so. We started with the SoC, dual A9 cores, tightly coupled into the fabric. And this was a revolutionary Zinc device, and I'm sure many of you have used it. We upped the ante again at 16 nanometers. There we went with 4 A53 processors from ARM, the most popular architecture in the world, by the way. And on top of that, we gave you both GPUs and video codec units, VCUs. As Victor mentioned, most recently, we've come out with the RFSoC device. By integrating ADCs and DACs, you really have a 5G radio on a chip. All you have to do is sprinkle a few more analog components, and you can be in 5G business. And really, if you look at the performance of those ADCs and DACs, they compare with the best in the industry. Gigasample per second, multiple gigahertz of bandwidth, 12-bit, 14-bit resolution. This is really good stuff. But in looking at that, to get to the next level, which is Versal, we obviously had to look even closer at some of the optimizations that we could do. So, what is Versal? So Versal is first and foremost, it's a 7-nanometer device. Comes to you from TSMC, who has the world's leading process at 7 nanometer. For those of you that went and bought an Apple phone recently, same technology. Clearly they don't have problems with yield. Let's leave it at that. On the other hand, from an approach perspective, Victor and Salil pointed out we're heterogeneous across the board. Our view is we're not going to restrict you by forcing you into one particular microarchitecture. And the reason for that is we don't have one prime application that we run. Think about GPUs. They were built for graphics. Let's be honest about it. Now they've sort of veered off into another direction, but in the end, the microarchitecture was optimized originally for graphics. So, let's look at where we got to. There are really 4 major sections within the chip. The easy way to think about it is we're going to go around in a clockwise direction. And starting with, of course, the scalar processing engines, which are the ARM cores, And I'll talk in detail about each of these blocks as I go through. The next one is our core fabric. We did a lot of work on the fabric. It is the thing that we're known for. It's the thing that we pretty much invented. So we should know the best way to take it to the next generation. And as I said, one of the things we noted is if you take your current generation and just scale it, it's not going to work very well. Third, we have, of course, the new intelligent engines. Part of that is our more traditional DSP that has been upgraded significantly. But then, of course, there is the AI engine. And this is a revolutionary technology. Last but by no means least, we're always known for connectivity. We connect to a range of different external interfaces, and we do it extremely well. Okay, so let's start our tour. Starting with the scalar processors, we've got the ARM A72. We have dual A72s in this design. Now that ups the single-threaded performance significantly over the A53s that we had at 16 nanometers. In addition to that, if you look at the throughput, it's about the same. So we really did, in this instance, go after single-threaded performance. We also have the OR5 cores. We had those in 16 as well. Those are real-time processors, just the thing you need if you're in autonomous driving and you need real-time response. And as Salil and Victor had mentioned, these also bring security and safety features that are very significant. And last but by no means least, and this is sort of the brains of the whole thing, but nobody will really see it in action. What you'll see are the side effects. And that's the platform management controller. So traditionally in FPGAs, you probably know, or in Zinc, you had to boot the processor, then you had to load the bit stream, and they were pretty much separate operations. Now we've combined that into one platform management controller, much more like what you would see with a CPU or similar product. So not only does the platform management controller take care of the booting and loading, it's also responsible for all the power management. It also takes care of things like dynamic reconfiguration, which is a really strong feature of FPGAs. The idea there is that you can have a piece of IP embedded in your fabric, living with a bunch of other IP close by. But you can switch out that one piece of IP without changing or interfering with anything else that's going on, and switch in another one, all controlled by the platform and management controller. Okay, let's talk about the fabric. So again, you know, one of the things that we decided to do was we said 7 nanometer real estate is the most expensive real estate in the world. Believe me, it's wicked expensive. So you have to earn your place on our chip. And so what that means is we threw everything out and we said, how would we put it back in again? Does it justify its existence? And I'll tell you an amusing story. So you know we have a quite sophisticated memory hierarchy. We have LUT RAMs, we have B RAMs, we have U RAMs. And you know, being the pointy-haired manager, I'm like, sounds like too many memories to me. So we discussed, well, let's see what everybody else does. Well, they use register files. Maybe what we should do is replace LUT RAM with register files. That sounds like a reasonable idea. I think I literally started a revolt. I went and talked to customers. I talked to our internal designers. They're like, you're crazy. You don't understand the problem. So we went back and looked a little bit more closely. And what we realized was that you, the developers, do amazing things with LUT RAM. And as a result, we realized, you know, it earned its place. We thought we would do what was the industry standard, but in reality, FPGAs are not industry standard in this regard. It was really interesting. I was having a discussion with a customer yesterday, and I was describing this problem to them, and they said, you know, you guys have application-specific memory hierarchy. And I realized that that's a really telling observation. One of the reasons why we do so well, as we said, in terms of machine learning. The other thing we looked at was, as we said, dynamic reconfiguration. In that perspective, I think we've improved the performance significantly. And I think you're going to see that if you're a person that uses that feature. I definitely recommend it. Okay, so now we get on to the intelligent engines. Again, as Salil pointed out, we have a number of different approaches as to how you can do machine learning. One is you can utilize the DSP within the fabric and build an incredibly custom implementation. You want 5 bits, you want 2 bits, you want 7 bits, you can have it. You can build what you want. But then sitting beside it is probably the most significant change architecturally in Xilinx in the last 15 years or so. And that's the AI engine. An array of VLIW SIMD cores, but connected in a very unique way. And I'll talk about that in a moment. And here they are, the AI engines. So what did we do differently from anybody else? Well, the first thing we did is we looked at it and we ensured that we had tightly coupled memory, because that really is important in this type of design. I think we heard Till earlier talking about the TOPS craziness, right? So I've been around a long time. I lived through the megahertz wars, believe it or not. And, you know, there was a time when the big CPU companies, which is how I used to earn my living, would say, well, I've got 400 megahertz. By God, no, I've got 426. I must be much better than you. What we all realized in the end was what really matters is delivered performance. And what was really important in those days was the memory hierarchy as well. So luckily, people invented the spec int and spec FP benchmarks. And what that did is it got rid of all of the megahertz discussions. And just as well, because in about 2000, as we realized, megahertz stopped increasing anymore. That was because Dennard scaling had fallen over and died. And so as a result of that, what I think we should be talking about is a new benchmark, and I think the ML-perf proposal that's going around right now is the right answer. So my prediction is that ML-perf will do to TOPS what spec did to megahertz. That's my prediction. Okay, so now let's talk a little bit more about how the core is enabled. So one of the novel things is that you can actually borrow memory from the 4 surrounding cores. They can actually share that memory. But we didn't stop there. What we said is, okay, why don't we give this particular array access to the fabric? Lots of memory down there. Maybe you can do something interesting with it on the way. And putting all of that together is what gave the remarkable results that Salil showed. And I think, you know, in the end, I hate to talk about the Clinton era, maybe I shouldn't, but anyway, it's the memory stupid, right? In the end, if you look at the utilization in other engines that have thousands of processors sometimes, probably 30 or 40% of them are being utilized. The remainder is silicon you're paying for that's doing absolutely nothing. So remember that. Okay, so the last piece about this, I think, is probably the most novel piece. So when this was being considered, we looked at why is our FPGA fabric so successful. The world is not just going to be ACAPs. It's going to be made up of a lot of devices. But the key thing that we want to see is that they can communicate effectively. So we, of course, support PCIe Gen 4, as do our current devices. In that regard, when we get PCI Gen 5, which we're still waiting for, then we'll upgrade to PCI Gen 5. No problems there. We have AXI-DMA, obviously integrated as well. And Victor had talked about the C6 consortium. And C6 really was a breakthrough from our perspective because we ended up starting the consortium with a group of 7 other companies, and now over 30 companies are contributing to that standard. It's 25 gigabits per second connectivity, full coherence. People like ARM, IBM, big names are supporting that. We also, of course, do memory controllers. For those of you that have known our parts for many years, you realize that the first thing you had to do if you wanted to build a processor subsystem related to the fabric, or if you wanted to just build something that had memory access, was you would have to go and get IP. It's a soft controller. Takes time, effort, takes LUTs, takes up area. What we realized was that to get the maximum performance and also minimize the cost to the end user, what we would need to do is harden the memory controllers, which is what we've done in Versal. So we have DDR4 running at 3200, LPDDR4 running at 4,266 megabits. And then we also plan to integrate high bandwidth memory when the appropriate one becomes available. Now, one of the interesting stories about HBM is that I'm not sure if you know, but all devices in production today that use HBM are built on the interposer technology that Xilinx pioneered back in 2010, 2011. So again, what we're doing is leveraging a lot of our history in order to offer the next wave of performance. So now let's talk a little bit about some other applications. We've talked an awful lot today about data center, and the reason we did that is my boss says data center is first, so I always do what my boss tells me. But let's talk about some of the other markets. Other markets that we support include wired, wireless, auto. Now, wired is a very interesting one. As I think it was Salil said, you know, one of the few exponentials left in the world anymore is machine learning papers, and I think we all experience that. But there's still a technology one left, and many people don't know about it, and it's called Nielsen's Law. And what Nielsen's Law says is that the bandwidth to your home has been increasing by a factor of 2 every 2 years for the last 30 to 40 years. That's a phenomenal capability, and it will probably continue. And you will continue to hate Comcast as a result, but so be it. But if you want to support that sort of data rate, imagine what that means, right? So, you know, from the protocol perspective, from the SerDes perspective, we have to double approximately every 2 to 2.5 years. So within the Versal device, we're going to have integrated multi-rate Ethernet Max. We'll also have interlocking, and of course, we'll also have cryptographic engines as well. This used to say crypto, by the way, but we decided it might be better to take it out because there are now bad connotations about Bitcoin. So we'll just move on from that point. Let's now look at the transceivers themselves. And this has really been a highlight for Xilinx in the last 3 or 4 generations. In 16 nanometer, we offer both 32 gig transceivers and 58 gig PAM4 transceivers. And if you go straight out the door behind, you can see both of those, or actually just one of them, actually 58 gig is being demonstrated in our product today. But in going to the next generation, remember said, we have to double. So we have 112 gig PAM4 transceivers in 7 nanometer. You can see a demo outside of a test chip that was developed for that. We show that at OFC, which is a big conference in the wired space, back in February of this year. World-leading performance, world-leading power. So in terms of connectivity in the SerDes space, we think we have you covered. Okay, so now let's talk about the RF side, and I'll talk a little bit more about this later. Remember that I said that in 16 nanometers with RF SoC, we had integrated the highest performance radio-oriented A to D converters and D to A converters available in silicon today. Given that, the integrated solution gives you a fantastic performance improvement, but it also gives you what some people miss is direct digital RF. So a lot of what used to be done in the messy analog domain is now being done in the digital domain, and we all know that's a much more tractable problem. So we also integrate digital down conversion, digital up conversion, and we support forward error correction and other standards that are needed to support either the 5G side of things, and DOCSIS is really the cable standard that goes along. It's sort of interesting what's happened in the industry. It used to be that there was a lot of work done in wireless to optimize for power, particularly at things about like digital predistortion, which you may have heard of. Now all of that is now leaking over, excuse the pun, into the cable side of things, and again, they're looking for the highest optimization in power because now they're using remote PHYs for cable. Okay, you're all familiar with our programmable I/O interfaces, no doubt. MIPI is becoming much more important. It's the way that you connect up cameras and displays and all those good things, and particularly now in-cabin in the auto industry, this is becoming a standard. The other area, of course, which we support is in terms of storage. And, you know, one of the most significant changes that I believe is happening in the data center is the disaggregation of acceleration. So we hear a lot about compute acceleration because it's sort of the sexy thing right now. But really, you have to accelerate the network, and you also have to accelerate the storage. Imagine, for example, in some of the things that Salil was talking about, that you have the bad guy or the bad gal, and you have their photograph, and you want to work out whether they exist in your database. One of the options is that you move all the data from storage. There could be, very large amount of images. You process them and see if you get a hit or not, and then back you go again. The other option is that you move that image down to the storage, do your comparisons, and then at the end of it come back with the result. That seems like a much more tractable answer in terms of what we're doing. Okay, last but by no means least, and I think this is last, we developed a network on a chip. So when we were talking about how we would architect the device, the one thing that I said is, I don't want to create a memory controller for my SoC, a memory controller for my fabric, another one for my AI engine. That just doesn't make any sense. Let's supply an array of memory controllers and make them available to whoever needs them at that particular time. Well, in order to do that, you have to have a very sophisticated way of communicating, and the way you do that is with a network on a chip. And this really, I guess, democratizes each unit, because to some degree they have access to all of the same capabilities that the other units have. And that, we think, is very important. Also, we have the ability to implement NOx in Fabric today. But if we look at it, we can get a significant improvement in power by doing a hardened NOC. We also get phenomenal bandwidth, exceptional latency, and we can also guarantee particular quality of service. And then again, as we said, it sort of ties the chip together. So this chip would not be what it is today without the NOC. So, I think I've gone over most of the markets that we deal with. You've heard a lot about cloud today. I talked to you about wired, so now at your next cocktail party, you'll know about Nielsen's Law, so you can tell people about that. In the wireless space, right, we've obviously talked quite a bit, and I want to give one more example there. But then also the endpoints, right? What's an endpoint? Well, an endpoint could be an intelligent security camera, or it could be an autonomous car. So there's a huge amount of variability there in terms of what the endpoint will be. So back to talk a little bit about how Versal addresses one of the leading problems in the industry at the moment, and that's 5G. So you may not know a lot about 5G because we've been talking about it for about 6 years, but we haven't really deployed it yet, right? Which is one of those problems with this technologies of the future. But finally, this year it is being deployed. In fact, it was deployed at the World Cup, and happily one of our RFSoC's devices was one of the devices that was carrying the 5G traffic. But one of the biggest issues that you have in 5G is you need 10x the bandwidth to deliver 10x the bandwidth to the kid on the street who's watching movies. Aren't we glad we're in this business? Nonetheless, in order to do that takes an incredible amount of technology. And one of the reasons is you can't increase the power. And the reason is that if you're up on the top of a pole as a radio in Abu Dhabi, you can't have a fan. It gets pretty hot up there. So you can't just quadruple the power. You just can't do that. So what you have to do is come up with a much more intelligent way of doing it, and the way people do that is with beamforming technology. And essentially the idea is simple, difficult to implement, but you can use the same carrier to direct, for example, information to the back end of the room, and then through an array of antennas and some fancy DSP, you get a very narrow beam that will home in on the user back there. Then using the same array and similar DSP, you can direct signal to the other side of the room on the same carrier. It's called carrier reuse or spectrum reuse. And you can get between 2 to 5x the utilization of the spectrum using that technology. The problem is it's incredibly compute intensive. Well, that's exactly what Versal was built for. So if we look at it, we believe that this capability, and again, we call it the AI engine, but in this particular case, it could be doing traditional digital pre-distortion and some of those other things. But as we also heard the gentleman from Nokia saying, we also need a lot of intelligence and machine learning there as well. A classic example of how Versal could work. Okay, so I've introduced Versal, the product. I'll finish by just saying we've had a huge amount of fun developing this chip. I hope you have as much fun using it. Thank you very much.